This is our lecture number 6. Today we are going to discuss about vibration produced in a string. Produced in a string. Here, see here, that is, suppose we consider string is fixed. Suppose string is fixed in between two rigid supports, and suppose we are going to vibrate this string, then as like air column, here at fixed ends always node is formed. Let me see, whenever string is going to vibrate, then at least one antinode and two nodes must be formed at the two ends. Suppose we consider this is the figure A. Now we consider same thing. Suppose higher mode, next mode, same string. Suppose this is the string having same length. Now suppose here one loop. We consider here two loops like this. Suppose this is figure B, and suppose we consider third mode here. Suppose L is the length of the string, and here we consider three loops like this. Three loops. That means we consider here. Here we have get two nodes and one antinode, means one loop. Here we get here three nodes and two antinodes, four nodes and three antinodes. And suppose here same length, L is the length of this string. Suppose we consider here N be the frequency, lambda be the wavelength. This diagram to be C diagram. Now N1 be the frequency, lambda 1 be the wavelength, N2 be the frequency, lambda 2 be the wavelength. Now suppose here in this figure A, suppose I will write here, in figure A, that is in both all figures, suppose we consider P be the tension in the string, M be the mass per unit length. Then here suppose V be the velocity, lambda be the wavelength. Then this all can be related by this equation, that is V is equal to 1 by lambda root T by M. Remember this equation directly. That is velocity in a string. Velocity of the waves in a string is directly proportional to tension and is inversely proportional to mass per unit length. And in this first figure, suppose we consider lambda be the length and we consider L be the length of this, then these two are related. Suppose I will write here for figure A, we get one loop, two nodes and one antinode, and distance between two nodes is always half of the wavelength. Therefore I will write L is equal to lambda by 2 and lambda is equal to 2L. Now here you know this relation, V is equal to 1 by lambda root T by M. Then we get here V is equal to 1 upon twice L. 1 upon, we consider here one correction, N equal to V by lambda. V V by lambda, and V can be given like this, 1 by lambda and V equal to root T by M. Then we get here N equal to, I will write N equal to 1 by lambda root T by M, or N equal to 1 by 2L root T by M, and N equal to 1N. This frequency we call it as a fundamental frequency. That is N equal to 1 by 2L root T by M. This is the fundamental frequency. Now we consider for figure B. In figure B, see here, 3 nodes and 2 antinodes. Therefore, 2 loops are formed. Then we write here L equal to lambda, or lambda equal to L. N1 equal to 1 upon lambda 1 root T by M, as like this equation, or N1 equal to 1 upon L root T by M, or N1 is equal to 2 into 1 upon 2L root T by M, or N1 equal to 2N. This is the next higher frequency. For figure C, suppose for figure C, we can write L is equal to, here you see, 4 nodes and 3 antinodes, 1, 2, 3. 3 loops are there, and length of one loop is half of the wavelength. Therefore, I will write here 3 lambda 2 by 2. Therefore, lambda 2 is equal to twice L upon 3. N2 is equal to 1 upon lambda 2 root T by M, and therefore N2 is equal to, we write the value here, lambda 2. That is 3 upon 2L, 1 upon lambda 2 means root T by M. N2 is equal to 3 into 1 upon 2L root T by M, or N2 is equal to 3N. This is next higher frequency. That means whenever there is one loop, N equal to 1N. 2 loops, N1 equal to 2N. 3 loops, N2 equal to 3N. That means as we go on increasing the number of loops, then we get here, suppose NP is equal to P plus 1 into N. That means in case of this vibration in a string, here we consider when string is fixed at both ends, then all harmonics are present. I will write here general statement. All harmonics are present. That means here we consider N equal to 1 means first harmonic. First overtone means second harmonic 2N. Second overtone means N2 equal to third harmonic 3N. Fifth overtone means P plus 1 harmonic. All harmonics are present when string is fixed at all, that is both ends. This is all about vibrations of air column. Now we will consider next article. That is laws of vibrating string. Laws of vibrating string. Here you know that is N equal to 1 upon twice L root T by M. This is the fundamental frequency in case of vibration of the string, and by using this relation we consider that is 3 laws. First law, that is law of length. What is the law of length? Here fundamental frequency or frequency of vibration of the string N is inversely proportional to length of the vibrating string if T and M are constant. This is the law of length. That is, frequency of vibration of string is inversely proportional to vibrating length when tension and mass per unit length are kept constant. Now we consider next law, that is second law, law of tension. Law of tension. Here, frequency of vibration of string is directly proportional to square root of applied tension if L and M are constant. This is the law of tension. That is, frequency of vibration of string is directly proportional to square root of applied tension when vibrating length and mass per unit length of the string is kept constant. Now we consider third law of linear density. Law of linear density. See here, n directly inversely proportional to square root of mass per unit length if T and M, if T and L are constant. That is, whenever tension and vibrating length of the string is kept constant, then frequency of vibration is inversely proportional to square root of mass per unit length. We call this law as a law of linear density. Now see here, this law can be extended. See here, mass per unit length M can be written like this: pi r square, this is the area of cross section, into, we consider unit length, and suppose rho be the density of material, then this can be written that is n proportional to 1 upon square root of pi r square rho if same thing T and L are constant, or we can write n proportional to 1 upon r and n proportional to 1 upon root rho if same thing T and L are kept constant. That is, frequency of vibration of string is inversely proportional to radius of that wire, and it is inversely proportional to, that is, square root of density of material of that wire. This is all about laws of vibrating string. Now we consider next article here. That is a sonometer. See here, sonometer, this is a hollow wooden box. Suppose I will draw here diagram. Hollow wooden box. This is the table. Now here, this is hollow wooden box. Now one end of the string is fixed here, and here we consider one pulley. This is the pulley. Then this is passed over this pulley, and to the other end we consider here, to the other end there is one hook. To this hook different weights can be applied, and here it is passed over these two knife edges. It is passed over these two knife edges, and we consider small paper rider. Small paper rider is placed on this wire. Also, a vibrating tuning fork is placed on this. We consider here, suppose vibrating tuning fork we can place here, and due to the force vibrations, this this wire starts vibrating, and whenever frequency of this tuning fork exactly coincides with frequency of this length in between these two knife edges, then paper rider falls down. That means here, due to the force vibrations, this wire starts vibrating. That means we consider this is the vibrating length L. Also this we consider M, mass attached, or we can write here T equal to M into G. This is the tension in the wire. L be the vibrating length, N be the frequency of this tuning fork, L be the length. Also we consider rho be the density, small m be the mass per unit length. Then you know this formula, that is T equal to 1 by 2L root T by M. In the fundamental mode, we consider here N equal to 1 by 2L root T by M. This L can be measured, T also measured, small m also measured, M equal to pi r square rho. R can be measured, rho means density of material of the wire. This also can be measured, and we consider Whenever paper rider falls down, that means at resonance, frequency of tuning fork exactly coincides with frequency of vibrating length of this wire, and we can easily calculate. Or by using this sonometer, there are different that is a number of uses of this sonometer. We will see one by one. Suppose we consider first use, that is a verification of first law of vibrating string. Verification of first law of the vibrating string. Here you see, suppose M can be measured, tension also known. Now we use number of tuning forks, N1, N2, N3, number of frequencies like that. And for each tuning fork, by same method, you can calculate the L1, L2, L3 like that. Now it is observed here that if we take this product N1, L1, N2, L2, N3, L3, then it is observed that this product comes out to be constant. That means NL equal to constant if T and M are constant. Here you put mass attached to the wire to be constant and M also constant, and therefore N proportional to 1 upon L if T and M are constant. In this way, that is first law of vibrating string can be verified. Now we consider second verification of the second law. Verification of second law of vibrating string. Verification of second law of vibrating string. Now here we see, suppose we consider L and M, we put the constant. We take small l and small m to be constant, and we consider here we use different tensions. Suppose we use N1, N2, N3. For that we use different tensions T1, T2, T3 like that. Then it is observed that N1 upon root T1, N2 upon root T2, we take these ratios, N3 upon root T3, then it is observed that these ratios comes out to be constant, and therefore we write N upon root T equal to constant if we consider here if L and M are constant, and therefore N proportional to root T if L and M are constant. In this way, that is second law can be verified. Now we consider next third one. Verification of third law of vibrating string. See here, suppose we consider, that is, we consider two wires having mass per units M1 and M2. Now here we consider, that is by using a tuning fork. Suppose first wire is subjected to the suitable tension and made to vibrate in unison with a tuning fork whose frequency is N. Now vibrating length can be noted. Suppose L1 be the vibrating length. Using the same fork, suppose we consider L2 be the vibrating length. Then it is found that is frequency vibration of two wires is kept same under the applied tension T. It is found that L1 into root M1, which is equal to N2 into root M2, or L root M equal to constant, and therefore we get here L proportional to 1 upon root M. L proportional to, then here you see, that is, we consider here another way. It is that is we get here L1 upon root M1. We take this ratio L2 upon root M2. Then this ratio comes out to be constant, and therefore L1 L upon root M comes out to be constant, or L proportional to root M. And you know this n proportional to 1 upon L from the first law, therefore n proportional to 1 upon root M if T and L are constant. Okay, in this way indirectly this third law can be verified. I hope you all understand this. Thank you.